Welcome to the deep dive. So today we're jumping into a really fascinating new paper. It argues that the core of today's LLMs, the transformer architecture, well, might be fundamentally flawed. Basically, it's struggling with information overload, and these researchers claim they have the fix. It's called the differential transformer, or DIF transformer for short. Now, the standard transformer, that's been the gold standard for years, but its whole operation relies on this thing called the attention mechanism. And the problem, according to this paper, is when you give it a really long document, it kind of gets lost, distracted.
That's exactly it.
Yeah.
When you actually look under the hood, visualize what's happening, the big problem is that standard transformers, they tend to over-allocate attention to irrelevant context. That's the term the researchers use. They call it attention noise. So what happens is the model ends up with a really low signal-to-noise ratio. The important piece of information, the actual signal you want, it gets buried in all the surrounding text. It just gets drowned out. They actually showed visualizations where the standard model gave a score of only like 0.03 to the right answer. And the noise, the irrelevant stuff around it, that got 0.51.
Wow. Okay, so 0.03 for the answer, 0.51 for the noise. That's basically designed to fail, isn't
And
it?
it almost guarantees errors in complex tasks. Yeah. It's just not efficient focus.
Okay, so let's get into this. If the issue is too much noise, the fix has got to be about getting rid of it. Our mission for this deep dive, then, is to figure out how this DF transformer works. How does this differential attention thing manage to, well, flip that signal-to-noise ratio? And crucially, what evidence do they have? Does it really make a difference in performance? So the core idea is differential attention. How does that actually work? Is it complicated?
It's actually quite elegant. Conceptually, the model calculates attention scores, but it does it as the difference between two separate attention maps. Both maps are calculated using the standard softmax approach.
Wait, it calculates attention twice and then subtracts one from the other?
Exactly. The whole point of this subtraction is to actively cancel noise. It encourages the model to develop these sparse attention patterns, focusing only on what's truly relevant.
Okay, that subtraction thing, it sounds almost like something from engineering.
It is. The paper uses that analogy. Think of noise-canceling headphones, or maybe more technically, differential amplifiers in electrical engineering. They work by measuring a signal in two places and amplifying the difference, which cancels out any noise common to both inputs.
Ah, I see. So it nulls out the background hum, leaving just the signal. That makes sense.
Precisely. It gets rid of that common mode noise.
So going back to those numbers, the terrible 0.51 noise versus 0.03 signal, did this differential method actually manage to fix that in their tests?
Oh, absolutely. Dramatically. In the same kind of information retrieval task, the DIF transformer assigned a score of 0.31 to the correct answer.
0.31. That's 10 times higher than the standard model.
Yeah, a tenfold increase in recognizing the signal. And the noise. They got the attention noise magnitude down to just 0.01.
0.01. Okay, so it basically eliminated the noise focus. That's huge.
It really is. It shows the model isn't just guessing anymore. It's actively focusing.
Right. And this isn't just some small adjustment then. It sounds like a real architectural shift. They're swapping out the standard attention module for this new differential one.
That's right. It's built to be analogous to the standard transformer, just replacing that core component.
So if the architecture itself is more focused, more stable, what does that do for model scaling? Does it change how big these models need to be or how much data they need?
It seems to change the scaling laws quite significantly. The research shows really promising efficiency gains, both in terms of the training needed and the final model size. Looking at their scaling curves, the DIF transformer seems to need only about 65% of the model parameters, or, alternatively, 55% of the training tokens, compared to a standard transformer to hit the same level of performance on language modeling.
Hold on, 65%. So you're getting the same results with roughly 2/3 of the resources. Can you give us a specific example, like comparing parameter counts? Developers always want to know that.
Sure. They found, for instance, that a 7.8 billion parameter DIF transformer, it performed as well as a standard transformer with 13.1 billion parameters.
Wow, okay, so 7.8 billion matches 13.1 billion. That's nearly half the parameters, right? About 59.5%.
Exactly. Almost having the model size for the same capability. Yeah. And that translates directly to, lower training costs, lower inference costs, faster response times, potentially.
That's a massive practical advantage. But what about handling really long texts, that deep reading capability? Context windows are getting huge now, like 64,000 tokens, even more. Can standard models even cope?
That's where standard models really struggle with noise. and where this differential approach seems to excel. They tested DIF transformer up to a 64K context length. And if you look at figure 4 in the paper, it shows this consistent drop in negative log likelihood for DIF compared to the standard transformer as the context gets longer.
Okay, negative log likelihood, NLL. Let's break that down quickly. Lower NLL basically means the model is better at predicting the next word, right? It's less surprised, understands the context better.
Precisely. A lower NLL indicates better comprehension and prediction. So that consistent drop for DIFF transformer means it's not just accepting the 64,000 tokens.
Yeah.
It's actually using the information within that massive context more effectively than the standard model.
Okay, if it's using 64K context effectively, it must nail the needle in a haystack test. That's the classic problem, right? Finding one tiny, crucial fact buried in pages and pages of text. How did it do there?
The results were pretty striking, especially when they made the task harder. For example, trying to retrieve multiple facts, like 6 needles in the haystack, within a 4K context. The accuracy difference between the two models ballooned to 30%.
A 30% gap, just from adding more distraction, essentially.
Yeah, favoring the DIFF transformer, of course.
Wow.
It suggests the standard model really struggles when noise increases.
It does kind of suggest the standard architecture might be, well, fundamentally limited for a reliable long context retrieval.
It's a strong claim, but the data points that way. And look at the really long context, the 64K test. When they put the key information deliberately deep inside the text, say around the 25% mark, the DIF transformer was 76% more accurate than the standard one.
76% better. Okay, that's not just an improvement, that's fixing a major failure mode.
It seems like it. It's tackling that catastrophic forgetting or getting lost in long contexts.
And it makes perfect sense, doesn't it? If the model's attention is wandering off to irrelevant stuff, it's naturally going to make factual errors or hallucinate. The paper links this directly, right? Bad attention leads to bad outputs.
Yes, they argue that this misallocated attention is a primary driver of contextual hallucinations, and they tested this on standard QA benchmarks like Casper and Hotpot QA, and also on summarization tasks like XSum, CNNDM. The DIF transformer consistently had higher accuracy, which translates to fewer hallucinations. The explanation is straightforward. It's just better at focusing on the essential information provided in the context.
That improved focus must surely impact how well the model learns during the prompt itself. What about in-context learning, ICO, where you give the model examples right before the question?
Yeah, the ICL results were also quite positive, particularly in many shot scenarios where you provide lots of examples. On classification tasks, the IFF transformer consistently beat the standard model. The average accuracy gains were anywhere from 5.2% up to 21.6% on some specific data sets.
Better learning is definitely good. But here's something I found really striking in the paper: robustness. We know standard models can be incredibly fragile with ICL. Like if you just change the order of the examples in the prompt, performance can just tank, right? It suggests the model learned the order, not the actual concept.
Exactly. That sensitivity to the order of demonstrations is a chronic headache for people building applications with ICL.
Yeah.
But the DFF transformer showed much less variance when the example order was shuffled.
How much less? Can you give us those numbers again? Because that sounds really important for practical use.
Okay, so on one data set, TRSE, when they randomized the order of examples, the standard transformer's accuracy swung wildly. The gap between the best order and the worst order was 19.0%. Huge difference. But for the DIF transformer, that same best to worst margin dropped to only 4.0%.
19% down to 4%. That's incredible stability. It means developers can worry less about meticulously ordering their prompts, doesn't it?
It really does. It suggests the model is learning the actual task from the examples, not just memorizing a sequence. It makes ICL far more reliable. And just to round that out, this focus also helped in math. Across 8 math reasoning benchmarks, by the end of training, DIF transformer was ahead of the standard model by about 11.3% in average accuracy. Focus helps reasoning too.
Okay, let's switch gears a bit to the really practical side, engineering, deployment, hardware. We talked about smaller model size, but are there other benefits for, say, running these models efficiently?
Yes, and this was one of the more surprising findings, actually. It turns out that the differential attention mechanism helps reduce something called activation outliers. These are like extremely large numerical values that pop up inside the model's calculations, and these outliers cause big headaches for quantization.
Quantization. That's about making the model run faster on smaller chips by using less precision, right? Lower bit widths.
Exactly, and these huge outlier values make quantization really difficult without hurting performance badly.
So how much does DIF transformer reduce these outliers? Is it a noticeable effect?
That's a very noticeable effect. They looked at the top one attention logits, which are sort of indicators of these maximum internal values. In the standard transformer, the max logit value hit 318.0, pretty large. In the DIF transformer, it was just 38.8.
Whoa, okay, from over 300 down to under 40. That's a huge drop. Why does shrinking that maximum value matter so much for quantization and speed?
Think about trying to represent a range of numbers using fewer bits. If you have one massive number like 318, it forces your whole scale to stretch way out, just to accommodate that one outlier. This means all the smaller, more typical values get squished together, losing precision. It's like trying to map a tiny village in Mount Everest on the same scale with limited detail. By bringing that maximum value way down to 38, the overall range is much smaller.
Ah, so you can use fewer bits, like 4-bit or even lower, much more effectively because you don't have those extreme values messing up the scale.
Precisely. You retain more precision for the important variations in the activations. And the results showed this. A 4-bit quantized DIF transformer performed about as well as a 6-bit quantized standard transformer.
Okay, 4-bit matching 6-bit. That's a significant step towards getting powerful models onto smaller devices, mobiles, edge computing.
Absolutely. It opens up possibilities for much more efficient deployment. Now, it's fair to ask, does the differential mechanism itself add extra compute cost? It does involve that subtraction step. But their initial implementations, using customized flash attention, show that the overall throughput is actually pretty comparable, maybe a small slowdown, like 5% to 12%, depending on the setup.
So a tiny potential slowdown for massive gains in focus, efficiency, robustness, and quantization friendliness seems like a good trade-off.
It certainly looks that way based on this research, yeah.
Okay, this has been a fascinating deep dive. Let's try to wrap it up. The core takeaway seems to be this elegant idea, subtracting attention maps to cancel noise. And this one change leads to a cascade of benefits. Better scaling, needing maybe only 65% of the resources. Much better retrieval, especially in long, noisy documents. Lower hallucination rates. And crucially, more robust learning, particularly for in-context learning. Less sensitivity to example order, plus easier quantization.
That sums it up well. I think the key conceptual shift here is moving from just optimizing what to pay attention to actively optimizing what not to pay attention to. It's about noise cancellation as a core principle. By getting rid of the junk, the signal becomes much clearer, leading to models that seem both smarter and more efficient to run.
So here's a final thought for you, our listener, to chew on. If the next big leap in AI performance comes not from processing more information, but from being better at ignoring irrelevant information, what does that really mean for the future of how AI understands and interacts with our increasingly noisy world? Something to think about. Thanks for joining us on the Deep Dive.